Okay, hi everybody. So today we're going to be learning about logistics, which is basically a mathematical model that can be used to help describe the rate of change of something, whether it be population or um, viruses or whatever. It will help model how things change. So logistics, use a logistical model to answer questions about the logistical growth. That's the goal. Okay. So logistics is just a type of a growth model. Okay, growth rate is proportional. So proportional is times k. Okay, not only to the amount present. So y is going to be the amount present right here, but also to the difference between the amount present and some other limit. Okay, which is this. By the way, before we get going very much further, I want to just quickly point out that this first portion of it, what we're doing is really just the explanation of what we're going to be using. You're not going to have to do all this every single time. So this first page and the next page and the next page, those are all just explanations. It's not really until you get to this page where we're going to be utilizing what we're using. So most of the times on the exam, you're going to be given something like from this page, which is actually pretty simple. Uh, but I know a lot of you guys like the explanation. Some of you don't, but I'm going to give you the explanation anyway. If you're really like, oh, whatever, just skip this video and go ahead to the next portion. Okay. So once again, we're dealing with some sort of logistical growth. Okay, what that means is it starts off like this and it kind of goes up slowly at first and then it gradually ramps up and ramps up, ramps up until you get to a point where like you start to slow down. So it speeds up and then it slows down. Now, why would that be the case? And by the way, this is like the point of inflection right there. So it goes from concave up to concave down. So why would it do this? So if you think about, for example, like a virus growth, when it starts off with one person, then goes to two, and then two to four, and four to eight, if everybody was just to affect another person. So it basically continues to go like that, and it grows, well, it seems to be exponentially, but then it gets to a point where it starts to slow down. Now, why would it slow down? Well, if you think about that, if you're in a room of like 10 people and it was growing exponentially, so it started off with one and then went to two and then four people and then eight, and then there's not very many more people to infect. And so at that point in time, we'd have to start slowing down because the number of new cases wouldn't be able to continue to go up. So it starts off slow and then it slows down. So this right here is kind of like the max of what it could be. And we call this the mark of saturation. You probably won't have to know what that is, but just in case. Okay. So anyway, so we go down here to what it more will look like. Okay. So this is the type of thing that we're going to have. And right here, this A, this is going to be what's called the carrying capacity. I do believe that you guys have had this in maybe biology or maybe even um, AP environmental. I'm not for sure. I'm almost certain it's in biology though. Okay, so A is going to be how much it could possibly go to. So if there's 10 people in a room, there's no way that more than 10 people could be infected. Okay, over here, this is going to be probably one of the bigger portions of what we're going to do moving forward because it's almost like always half of what the carrying capacity is. And you'll see what I mean when we get going on this. Okay, and once again, this is a point of inflection. This is the point we're going to start. So T naught is going to be the time where we started, and Y naught is going to be that initial point or that initial population or whatever it is. Okay. Anyway, next page. Okay, so in order to derive the formula, and the formula is going to be given on this page right here, we need to solve this using separation of variables. Okay, now separation of variables is something that you will have to know how to do. So even though you won't have to do separation of variables for logistic growth, most commonly or most certainly you won't have to, you will have to know how to do or solving a differential equation by separation of variables. Okay, so we're going to separate this. So separating, remember, you have to first figure out where your two variables are, and it's given by the y and the t, so the dy and dt. And what I want to do is get all the t's to one side of the equation and all the y's to the other side of the equation. Well, you notice the only thing with the t is here, so I'm just going to multiply this up and I'm going to divide this down. The problem with just dividing this down though is it's going to look pretty funky, so I'm going to clean this up a little bit. So I have k, y, just distributing, minus k, y squared all over a. So I have a fraction minus a fraction. So I'm going to combine them together. Least common denominator is a. So I have a, k, y, minus k, y squared all over a. Okay, so now I'm going to flip and multiply this to the other side, and I'm going to multiply the dt up to the other side. So in doing so, I have a, k, y, minus k, y squared all over a dy is equal to dt. And, oh wait, I didn't forgot to flip this. My apologies. So let's go ahead and go over here. So you have a over a k y minus k y squared dy is equal to dt. Okay, sorry about that. Okay, so I've separated the variables. Now what I want to do is using partial fractions, yes, partial fractions, I'm going to rewrite the fractions, okay? So I know I need to do partial fraction in this portion, so I have to figure out how to do this. And remember that one of the best ways to do this is factor what's on the bottom. So I'm going to go ahead and do that. So I'll just go right here. So factoring what's on the bottom here. I can take a ky out of both of these, and I'm left with a minus y dy is equal to dt. Okay, so I'm going to split it apart. Now, I normally use a and b, but there's already an a here, so I'm going to use b and c. So I have b all over k y minus or plus c all over a minus y, and that should be equal to a all over k y a minus y. Okay, so finding common denominator and adding them together, and once again, ignoring the denominator, I have b times a minus y plus c k y is going to simply be equal to a. Okay. Now, remember the trick is to pick a clever value of y that we plug it in will make it go away. Well, when y is equal to 0, that will go away. So letting y equal to 0, this gives me, so this will go away, that will go away. You have BA is equal to A, so B is equal to 1, because that's what I was trying to solve for. Okay, and then furthermore, we're going to let y be equal to, now here I need to make this go away, so if I let y be equal to A, then this will go away, and then I'm left with, let's see, C, K, A is equal to A, so therefore C is equal to 1 all over K. Okay, so I'm going to come back up here, and I'm going to rewrite this differential equations, but using my new B and C values. So this is going to be B, which is 1, so 1 all over K, Y, plus C, C is 1 over K, all over A minus Y, dy is equal to dt. Okay, so we just rewrote it, and we rewrote it that way, so now we can integrate both sides. Okay, so coming down here and integrate both sides. So I have, I'm going to factor out the 1 over k. So I have 1 all over y dy plus factor out the 1 over k again. I have 1 all over a minus y dy is equal to the integral of dt. So I have 1 all over k. This will be ln of the absolute value of y plus 1 over k times ln of the absolute value of a minus y is equal to t plus some constant. Okay, now notice what I want to do is here is I'm trying to solve for c. I'm trying to figure out what c is equal to. There's a lot of stuff that's going on here, and I also have this k value, which I don't quite know what it is yet. but I'm going to rearrange things. So I'm going to multiply everything through by k. So I'm going to utilize the property of logarithms. If you have log of y plus log of a minus y, then you can add those two together. Oh wait, I just missed a spot though. Going from here to here, I goofed up. Where did I go wrong? So the a minus y, it is ln of a minus y, but by like the reverse chain rule, you have to divide through by the derivative of the bottom here, or the derivative of this, which is -1. So this should actually be a negative there. Okay, so let's go down here, multiply everything through by k. So I have ln of the absolute value of y minus ln of the absolute value of a minus y is equal to kt plus. Now k is a constant, c is a constant, so when I take k times c, I get another constant, so I'm just going to call that c1. Okay, utilizing the laws of logarithms here, the negative, I'm going to rewrite this as ln of the absolute value of y all over a minus y is equal to kt plus c1. Okay, exponentiating this, you have y all over a minus y is equal to e to the kt plus c1, which is equal to e to the kt e to the c1. Now e is a constant, c is a constant, so that's just another constant. So this is equal to e to the kt times some constant c2. This is the c that I'm going to try and solve for. Okay, that was what the original problem was asking here, is it's solve for c. Okay, so I'm just going to rewrite the equation. So I have y all over a minus y is equal to c2e to the kt. Now, I'm going to plug in a value that I know, and I'm going to say at t is equal to 0, my initial population is going to be y is equal to y naught. So that gives me the coordinate 0, y naught, and I'm going to plug it into that equation. So I have y naught all over a minus y naught is equal to, plug in 0 here, this goes to 0, e to the power of 0 is 0, so that is just simply c2. Now, if you look ahead, my c value is y all over y naught minus a. Why have a minus y naught? So what happened here is I can factor a negative out of here. So I have y naught all over negative y naught minus a is equal to c2. Multiplying both sides by negative, I have y naught all over y naught minus a is equal to negative c2, which is just another constant. I know. So it's c3. So now I have my c value is equal to y naught all over y naught minus a, which is what we have on this page right here. Okay, now I'm actually gonna try to use this to solve for this, to figure out what y is. Okay, so I'm gonna go to the next page, and I'm gonna rewrite where we are at. Okay, so I was at, let me bring this back over. I'm gonna go right here. I'm gonna utilize this to solve this. Okay, so in doing so, I have y all over, and I'm actually going to switch it around right now. I'm going to take out a -1 here and pass it up there, so it's going to be c3. So I have y minus a is equal to c3 times e to the kt. And now what I want to do is I want to solve for y. I want to solve for y. So multiply this up. So I have y is equal to y minus a times c3 e to the kt. Distribute. So y, because I have a y over here and I have y over there, and I'm trying to solve for y, so I need to get them to the same side of the equation and then factor it out. So y is equal to y c3 e to the k t minus a c3 e to the k t. Subtract this over. So y minus y c3 e to the k t is equal to um, negative a c3 e to the k t. Um, divide everything through by -1. So I have y c3 e to the k t minus y is equal to a c3 e to the k t. Factor out a y. c3 e to the k t minus 1 is equal to a c3 e to the k t. Divide through. So y is equal to a c3 e to the k t all over c3 e to the k t minus 1. Okay, now let's take a look what we're trying to get to. We're trying to get to that. Oops, trying to get to that, which looks nothing like that. But if you notice, the top only has an a to it. So what I'm going to do is I'm going to try and cancel the c3 in this, and I'm going to do that by factoring it out of the bottom. So this is equal to a c3 e to the kt. I'm going to factor a c3 e to the kt out of this, which is c3 e to the kt. And when I take out of this, I'm left with 1. And minus 1. When I take c3 e to the kt out of 1, I'm left with 1 all over c3 e to the kt. Cancel, 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 cancel. So this is equal to a all over 1 minus 1 all over c3 e to the k t power. Let's go back and see if that's what we're trying to find. Well, we have it written here as a negative power. Ours is as a positive power. So we can go ahead and bring this up. So this is equal to a all over 1 minus e to the negative k t power all over c3. Okay, and this is where c3 is equal to, so where c3 is equal to y naught over y naught minus a. Okay, so I've completed the derivation of it. Okay, so now you just need to know this, and you do have to have this memorized. I'm sorry, but you have to spend a little bit of time to go ahead and memorize what this is. Okay, next page. Okay, so memorize or do what we did. Okay, so you either have to memorize this, or you have to go through the derivation. You have to memorize this, or you have to go through the derivation of it every single time. Okay, so I'd rather not, right? Okay, so let's do some examples now. Okay, so example, solve y prime is equal to 0.3y 4 minus y with the initial condition this. So we are going to do separable differential equations here. Okay, so we need to hold on, sorry. Oh, so the first thing we're going to do is going to rewrite it so it matches this. Okay, we're going to take this and we're going to try and write it like that. Okay, so I have y prime is equal to 0.3y times 4 minus y. Now, if you notice, we have this is 1. So right now it's 4. I need to be 1. So factor out the 4. So you have y prime is equal to, so bring out the 4. 4 times 0.3. Well, 4 times 3 is 12. So 4 times 0.3 is 1.2. So 1.2 y times 1 minus, now when you take a 4 out of y, you're left with y all over 4. Okay. And so identifying what k and a are, okay, looking back up here at this equation, k is just the first constant. So this is 1.2, and A is 4. And by the way, we should actually take a moment to talk about what A is. So A, if we go back to our original page, A is the carrying capacity. That's how much, as you go on forever and continue going, go forever, it's going to approach A. Okay, so that's what the carrying capacity is. Um, K is what's called the growth constant, but we're not going to really deal with that too much. Okay, so going back to what we're dealing with. Okay, so now we need to find the value of C. So remember, the value of C is given simply by this equation. So C is going to be equal to, well, what is my initial Y value? My initial Y value comes from this coordinate right here, and this coordinate is 0, 1. So I have 1 all over, and then it is 1 minus A. So 1 minus A is 4. So this is negative 1/3. So now I'm just going to come and I'm going to rewrite this equation using all this information. So I have Y is equal to A, which is 4, all over, let's get to that equation, 1 minus e to the negative k, and k is 1.2, so negative 1.2 t all over c, and c we've determined to be negative 1/3. So this is negative 1/3. Okay, so just cleaning this up, I have y is equal to 4 all over 1, negative times the negative, so plus, I'm going to flip and multiply 3e to the negative 1.2 t. Okay, and that's it. Okay, next page, next example. Okay, so this is the type of question that you'll see on the BC exam. Okay, so a 10,000 acre forest has a carrying capacity of 1,000 deer. So if you were to graph this logistically, up here is going to be 1,000, and the graph will go like this to goes there. Okay, so assume that the deer population grows logistically, where growth constant is K. Find the deer population if the initial population is 100. So this value right there is 100. So the differential equation is, so if you go back to what the equation is for differential equation right here, we're going to take that equation to rewrite it. And eventually, like I said, we do need to know this by heart. So we have dy dt is equal to k. K in this instant is 0.4. So we have 0.4 times y times 1 minus y all over the carrying capacity 1,000. Okay, so that's just rewriting it in that form. Okay, so how long does it take to reach 500? So now, if we wanted to reach 500, I want my y value to reach 500. That means I want to go right to this equation right here and utilize this one. Okay, so what do I have to find? I have to figure out what c is, right? So let's first do that. Let's figure out what c is going to be equal to. So c, by this equation right here, is equal to y naught, which is my initial population, which we've said is 100, all over 100 minus the carrying capacity of 1,000. So this is 100 over negative 900. So this is negative 1/9. So that's the c value. Okay, so now we can go ahead and plug it into this equation. So I have, let's just go right below this. I have y is equal to a, which is a carrying capacity of 1,000, all over 1 minus e to the negative k. Did I determine what k is? It's zero point 0.4. Oops, zero point 0.4. So 0.4 t all over your c value, which is negative 1/9. Okay, so I'm going to go up here. So y is equal to 1,000 all over 1. Negative times a negative is a positive, so plus. Once again, I'm going to flip and multiply. 9e to the 0.4 t. Okay, so now all I need to do is figure out when it's 500. So I have 500 is equal to 1,000 all over 1 plus 9e to the 0.4 t. And then I have to solve for t. So this we will not do by hand. We'll have to do this using our graphing calculator. I've already done it. Make sure that you guys do know how to do this. And so when you do this, you get t is equal to 0.5493 years. Okay, notice that I went past the 3 decimals just to make sure that it's accurate, which is totally fine. Okay? Okay, the next one. What is the limit of p of t? P is the population of the deer. What is the limit of p of t as t goes to infinity? Well, that's just the carrying capacity. So the answer is 1,000. Okay, that's typically the easiest one. Okay, next example. Okay, so we have a multiple choice here. Okay, so the population PT satisfies of a species satisfies the logistical differential equation dp dt is equal to p times 2 minus p over 5,000, where the initial population is 3,000 and t is the time in years. What is the limit as t goes infinity? Remember that the a value is just the carrying capacity. So what they're trying to trick you into thinking is that the answer is 5,000, but it is not 5,000 because the formula is 1 minus. So you have to factor out a 2. So factor out a 2, you have 2p times, 1 minus p all over 10,000. And so the carrying capacity is 10,000. Okay, be careful with that. And then notice right here, your k value would be 2. That'd be the growth constant. Okay, so down here, the number of moose in a national park is modeled by the function m that satisfies the logistical differential equation, this, where t is the time in years and n of 0 is equal to 50. So your initial population is 50. What is the limit as t goes infinity of m of t? Okay, well, it's already in that form, right? And that's your carrying capacity, so the answer is just B. That one was easy. And these are typically the types of questions you'll see with logisticals growth. Okay, and then last page. Okay, so this is a little bit more difficult. Okay, a certain rumor is spread through a community at the rate of dy dt is equal to 2y times 1 minus y, where y is the portion of the population that has heard the rumor at time is equal to t, or time t. What proportion of the population has heard the rumor when it is spreading the fastest? So if it's spreading the fastest, what does that mean? That means the rate is going to be the maximum. So that means the rate of the rate will be equal to 0, right? When you try and find the maximum, what do? Take the derivative set equal to 0 and solve. But in this case, it's the second derivative because we're trying to find the rate at which the rate is spreading the fastest. So I first need to calculate the second derivative. Okay, so A. So first I'm going to rewrite this as 2y minus 2y squared. So then the second derivative of y with respect to x is equal to 2. But remember, I am taking the derivative with respect to t. Oh, this is wrong. This should be t. I'm taking the derivative with respect to t of y. So when I do this, I have 2, and then the derivative of y is 1, but then I have to have the y prime there. Okay, and then minus 4y y prime. Now the nice part is I know what that is. Okay, so this is equal to 2 times y prime, but y prime is 2y times 1 minus y minus 4y times y prime, which is 2y times 1 minus y. Okay, let's clean this up. So we have, so this, and then times that is going to give you 4y, and then that times that is going to give you minus 4y squared. Okay, minus that times that gives you 8y squared, and then that times that is going to give you plus, because negative times a negative, 8y cubed. So this is 8y cubed minus 12y squared plus 4y. Okay, now I want to know where that's going to be the fastest, so I got to set it equal to 0, and I have to solve. So let's see. I'm going to go over here. So I have 0 is equal to, notice how they all have a 4. Notice how they all have a y. And so this is going to be 2y squared minus 6y plus 1. Um, hold on one moment. Well, um, so if you notice, this causes issue, right? Like you can't factor this. At least nicely you can't. So perhaps there's a better way to do this. Let's actually go back up to this spot right here. And let's take a look. Okay, so I worked forward, I got to this spot, and I was like, oh crap, that's not very good. So how else could I do this? Well, what do you notice? They both have a 1 minus y to it, right? So let's do this a different way. And this is fine, there's nothing wrong with this work. But let's just do this a different way. Let's factor out a 1 minus y out of this. So if you take out the 1 minus y, you can be left with 2 times 2y minus 4y times 2y. So that gives you 1 minus y times 4y minus 8y squared. Well, that's really nice. That's nice how that worked out. Oh, that's what I did wrong up here. Actually, it would have worked out the same way. I apologize. Oh no, that works there. Yeah. Okay, so let's go here. And once again, we want to set this equal to 0 and solve. So this is going to give me 1 minus y is equal to 0. So y is equal to 1. Or it's going to give me 4y minus 8y squared is equal to 0. Factoring out a 4y, I'm left with 1 minus 2y is equal to 0. So y is equal to 0, and y is going to be equal to a half. Okay, so now we need to determine where it's going to be the max or the min values. So let's go ahead and do this on a number line. And so I have 0, 1, and a half. So 0, a half, and then 1. And I need to plug this back in to the thing I was taking the derivative of. Okay, so in plugging in these values, now we're only worried about time moving forward, right? So let's plug in a value here to like a quarter. So I'm plug it in here, and I'm gonna let you guys go and verify this later. This turns out to be a positive. So you pick like a fourth and plug it into here. That's gonna be in a positive value. Okay, you plug something between a half, so like 3/4 into this. Well, it turns out that that's going to be a negative value. and then plug in something bigger than 1, it's going to give me a positive value again. So I want to know when it's its fastest. So it's growing when it's fastest is when it goes from increasing to decreasing. So it goes from up to down, the slope does. Okay, so this is going to be a relative maximum point. So y is equal to 1/2 the population is growing the fastest. Okay, so B. Okay, if at time t is equal to 0, 10% of the population have heard the rumor, find y as a function of t. Okay, so that's where I have to go back and I have to figure out what this equation is right here. This equation right here. Okay, so I need to figure out what A is, and I need to figure out what C is going to be, and then K. So kind of all of it. Okay, so let's take a look at the equation that I'm given. Okay, so this is the equation that I'm given right here, which I could rewrite as 2y times 1 minus y all over 1. So it tells me what y is, or sorry, k is, and it tells me what my carrying capacity is. Okay, so 1. So what does it mean to be a carrying capacity of 1 for rumors? That means everybody's heard it, because we're dealing with the percentage of the population. Okay, so going down here, I know that k is going to be equal to 2, and then I need to figure my c value. So c value is going to be equal to the carrying capacity, 1, all over, sorry, so yeah, the carrying capacity all over 1 minus, I apologize, this is initial. Okay, this is going to be the initial population. So the initial population at time is equal to 0, 10%. So these are going to be 0.1. Okay, and then minus A, which is my carrying capacity, which is 1. So you have 0.1 all over negative 0.9. So this is negative 1/9. Okay, so going to our equation then and rewriting it, I have y is equal to A, which is a carrying capacity, which is 1, all over 1 minus e to the negative k, so 2t, all over negative 1/9. So this is going to be equal to 1 all over 1 plus 9e to the negative 2t. And that's what the formula is going to be. Okay, so C states, at what time t is the rumor spreading the fastest? Okay, so the rumor spreading the fastest is, and let's go back to our picture of the logistical curve. Sorry, just scrolling through my papers. Okay, so you go through here, and it's spreading the fastest at the point of inflection, or whatever half of the carrying capacity is. That's when the slope of the tangent line is the max. So in other words, if the carrying capacity here is 1, then when it's spreading the fastest is when it's equal to a half. So what I have is I have a half is equal to 1 all over 1 plus 9e to the negative 2t. And then using our graphing display calculator, we have t turns out to be equal to negative 1/2 ln of 9, just solving it for t. Okay, and that concludes it. We are officially done with all of our content for Calc BC. Congratulations, now time to prep for the exam.